Hi, welcome to the classroom. Today we're going to be talking about soldering. It's a skill that's very useful if you're going to work around in electronics. Whether you're looking to add connectors to a sensor board that you bought or build your own circuit boards from scratch. We'll talk you through how to do that. I'll show you some demonstrations, teach you about the tools and the techniques, and then I'm going to give you an assignment to go home and practice it yourself. So let's get to it. So here's a basic layout that I like to use for soldering with some of the main parts that I'll often use, tools and whatnot. So looking around the bench, there are a lot of pieces on here. Some of them are optional, just kind of make it nice and easy. Some of them you really got to think hard about making sure you have. At the bottom, this gray pad here is called a static mat, and it's actually connected through a ground wire over here that's just off your screen. And what it does is that as static electricity builds up and contacts this has just a little bit of conductivity to it. So the static electricity will distribute across this to the ground wire and then dissipate off. Static electricity, like I've talked about in the past, can really damage components. Now, do you need this? Not necessarily. I worked for years and years without one. Even when I was fixing TVs for a living back in college, I didn't generally have a static mat. But with small modern microelectronics, your odds are a little bit higher that you end up zapping it and damaging a part. So if you're going to do a lot of soldering or work with a lot of components, you might want to think about getting a static mat. This bench top here is just a bench that I made up out of parts from Lowe's. Really any horizontal surface will do. You probably want one that doesn't matter if it gets a little bit scratched up. If you're soldering on your mom's kitchen table and you melt through it and burn it, she probably won't be very happy. If you're not going to use a static mat, if you're not going to have a surface like this that you can beat up on a little bit, you're going to want to have something like a piece of wood that you can lay down to provide a protective cover that's not going to melt. Wood will char and kind of turn black and brown, but it's not going to like melt and like get down into stuff. So something to think about. Other stuff that I have here, this is a magnifying glass that also happens to have a light on board. Now when I was younger, it wasn't as important. Eyes are pretty strong and good, you could see up close and the light didn't matter so much. But as you get a little bit older, it gets really important to have enough light. And frankly, sometimes a lot of the pieces we work on, like this microcontroller, are small enough it's really hard to see. So I can position this light in such a way that I really can get a good idea and good look at what I'm doing with the components. The extra light's helpful, the magnification's helpful, and if I don't want it, I just put it up out of the way. Over here is my soldering station. There's a controller box here that sets the temperature, and then the soldering iron itself, and then just a rack with a chore boy that I can use to clean the tip, and we'll talk more about how to do that later. This is called the third hand, and basically all it is a bunch of clips on little bendy things that you can connect parts and pieces to and hold them in place. One of the things I've found is that 9 times out of 10 when I'm soldering, stuff doesn't want to stay put the way I need it to, and I need a third hand because I'm going to have solder in one hand, my soldering iron in the other hand, and then there's the part and the board and all those pieces that I'm trying to keep all together and balance them out. For years and years and years, I just kind of messed with it, did the best I could with my hands, and sometimes the results weren't super great. These are only a few dollars. You can find them on Amazon or eBay or any number of places. I think they're worth the work. I like the ones that have a little bit longer arms that are more flexible. There are some that are just like a horizontal bar with 2 little clips that stick up that you can hook on to the components. This is a little more flexible. Use it a little more widely. Other things I have paper towels. I don't use those so much for soldering, but in general I like to have them handy. This is solder flux. We'll talk about that in a bit. Solder wick, and then I have 2 different sizes of solder spooled up and ready to go. So that's kind of an overview of the bench itself. And we'll walk through some of the other tools and bits and bobs that we'll be using for soldering here in just a second. Alright, so the first thing we're going to talk about are some of the tools that we're going to use. I already talked a little bit about the third hand, and I showed you the soldering iron briefly. But there are other tools that are super important if you're going to be successful with soldering. One of the most important is a pair of flush cut-off wire cutters, these things. They're designed so that this surface here is nice and flat and can be get right down under the surface of the board and clip wires. This particular pair is only really strong enough to clip pretty thin wires, but it's really, really good for clipping off resistor leads after they've been soldered in, or the excess lengths on pins if you're soldering pins to a board, or wires if you're attaching those. I use these for all kinds of things. I actually bought probably a half a dozen of these the last time I ordered them for a few dollars a piece. So when I break them, lose them, melt them, ding the blades up, doesn't really matter. I just pick up another pair and move along. The next most important tool is a pair of small needle nose pliers. These pliers I bought probably 25 years ago from a specialty tool store. These are designed specifically for bending wire, small wires. However, you can use just about any small pair of needle nose you can find. Whether that's something you pick up at a place like Harbor Freight, Lowe's, or Home Depot, or a specialty tool store, they're all going to work roughly well. And one of the main things you use these for is bending wires and leads on components so that they fit the holes that you got to put them into. And it helps to dress up the connections and the wires to make them look half decent and to make them fit right. Another tool I use regularly is a dental pick. Don't use these for my teeth, but they're very important for me when I'm working, especially with small surface mount components. So I can use them to hold them down. I can use them to manipulate and push surface mount components around on the board. If you're just working with like through lead components, like big resistors or transistors that are in discrete packages, not super important. But I will say that it comes in useful in ways you hadn't really planned on. Other parts and tools that I use. I usually have a brush. Sometimes it's a toothbrush, sometimes it's one of these acid brushes, and I'll use this with alcohol, usually just standard rubbing alcohol, to clean off solder flux or just kind of clean up any mess or sticky goo left over when we're done soldering. Another piece that you'll end up using a fair bit are wire strippers. This is one style, and this is another style. These ones here are more commonly used for kind of industrial applications. You see mine are a little bit rusty because they've been in my outside toolbox, and I haven't really taken good care of these ones because I don't use them very much. I'll use these when I'm wiring a trailer or a car. That's about it. Most of the time I run to this particular pair here. You'll also find ones that have a couple of preset sizes on the front, kind of like the middle of this pair here, but it's on the jaws of the tip. Those work pretty well for many applications. I just don't have a pair and I don't really use them. I really like this style here. So the way this one works, you've got the cutting grooves here, and then this wheel right here sets how far the jaws can close. And I don't know if you can see it or not, but right here is a line that's in a number 18. That's for 18 gauge wire, and there's a corresponding line right there in the plier. And if I want to strip a larger wire, so the smaller the gauge number, the bigger the wire, to 14 gauge, I can move it right there, and it'll restrict how far this closes. So I can grab around, a hold of the wire, cut the insulation, and then pull it off. We'll go over specifically how to use these later, but again, a very important tool, especially if you're attaching wires and leads. The soldering iron itself, there are a couple different components. I already pointed out that there's the temperature controller on mine. Yours may or may not have that. It depends on what you get. Some of them you just plug them in and it runs the temperature that it's going to run. I do recommend that you go ahead and spend a few dollars to get one that has a temperature control. If the iron gets too hot, one, it'll burn the tip up, and two, you're much more likely to heat the parts up too much and cause some real damage. So on this one, there's this top part unscrews, and inside is a heating element right here. This is what actually gets hot. The tip fits over the top, and the tip's interchangeable. So this is a pointed tip, and then I have a handful of other tips right here that have different characteristics, and you use these for different applications. This one right here has a very, very fine pointed tip. It's great for getting in around small components like surface mount components, microchips, things like that, where there's not a lot of room. And oh, by the way, where I don't want it to heat up very fast. The amount of heat that the soldering iron puts into the part and how fast that heat goes from this soldering tip to the component depends on how big the area is it touches. When it's a tiny little point like that, the heat moves pretty slowly and you're less likely to overheat things. This tip is very much the other way around. It has a large flat surface here, nice and thick, so the heat's going to move very quickly from the iron down into the component. This one I've never used. I don't have an application for it. I suppose if I was trying to solder like stained glass or something, that might be useful. This gigantic wedge tip, again, not one I've ever used, but it's designed for soldering big heavy things when I need to put a lot of heat into it in a hurry. This is more of an average tip. This is probably where you're going to start with most components. You want something about like this, either a wedge or a small flat, but not anything like these two here. You select the tip based on what you're soldering. Also, I will say that the one that's on here now, I've used this for almost everything for the last, I don't know, 7 or 8 years. But once to change out the tip, you unscrew the cover, pull the tip off, slide the new tip down on, screw the cover back on, and you're good to go. I'm going to set these tips aside because I'm not going to be using them. The soldering iron itself will have a grip down here. Most of them will have like a silicone rubber because you don't want anything that's going to melt. You do need to make sure that's reasonably tight on here, because if you don't, it'll loosen up as it heats and cools. This is flux paste. Flux in general is a chemical that when you heat it up with the metal, it'll actually eat off or clean off corrosion or things like that would interfere with a good solder joint. This is just a kind of whitish paste. A lot of flux is actually rosin, like tree sap that's been hardened up. The same kind of thing that a violinist would use on their bow to make it vibrate the strings well. Now, I only really use the flux paste with surface mount components. If you're working with discrete components, so resistors and transistors that are big enough you can grab a hold of them with your fingers, the rosin core that's in the flux that's inside the solder is good enough. Now, inevitably, you're going to screw something up. You're going to have to undo it, and you're going to need to get rid of solder and move that you put down. This is called solder wick. It's a braided piece of copper. If you look here, you can see that the braids are loose a little bit. And then inside of coated along with that is some rosin flux. Now, if I heat solder up and I touch this wick to it and I heat the wick up, it'll actually wick the solder up in. You can see right here, there's a bit where the solder's kind of pulled up in here and it's made this hard and rigid. That's how I'm going to pull solder off of a board or off of a component when I need to undo something that I've just done. Very good to have around, otherwise it's pretty tough to get solder out. Another tool you can use to undo a solder joint, pull solder off of a board or off of a component, is called a solder sucker. That's what this lovely little thing is. And basically what you have in here is a little spring-loaded plunger. When I'll cock it in, now there's this plunger that's captured down here. This is a Teflon tip that doesn't melt particularly easily. And what you'll do is you'll use the soldering iron to heat the solder up, put that right up on the solder, and then hit the button, and it'll suck the solder back up in. If you open it up, you'll see that there's kind of silvery crud. That's solder in the past that I've had to undo. I don't use this a whole lot. I used it a little bit more when I was fixing TVs, but mostly now it's a curiosity for me. I'd rather use solder wick for almost everything. If you have one, great. If you want to buy one, go for it. I don't have a whole lot of use for them. Alright, let's go ahead and talk about the breadboard. This piece of white board is called a breadboard. I don't know why they call it that. It's been that way for a long time. And what a breadboard is it's a prototype board, really, where we can wire up circuits temporarily and interconnect components to test whether they're going to work the way we want them to run experiments without having to solder components and build custom circuit boards. The way these are set up, you have a series of holes, right? Each of these holes are evenly spaced at 1/10 of an inch, so there's 10 holes per inch. It's a pretty standard measurement for electronics. The pins on my Arduino here are 1/10 of an inch apart, so they line up perfectly with these holes in the board. Now, orientation wise, this piece right down the middle, this kind of divot, is called a channel because it kind of looks like a channel. That separates this half of the board from this half of the board, so there's no electrical connection between anything here and anything here. That's important because if I have like an integrated circuit or like this microcontroller here that's plugged in, I don't want this pin automatically connected to that pin or this pin connected to those ones. I want to be able to manually control where those are connected. The next pieces are these sideboards that run along here. See the blue line and the red line. Along this line, all of these holes are connected together inside. So if I put a wire in this hole right here, it'll also, and a wire in this hole back here, they'll be connected together. Any wires inserted in any of these holes are all going to be connected to the same place. The same thing will happen with this red one. All of these are connected together. Usually you're going to use that for power. So your red line, when you see there's a little plus right here, you'll often use that for your positive power. The blue line, or the minus, usually use that for ground. There's some places where it might be a negative voltage. There's some places you might use it for something else, but that's usually what you're going to do with it. When you get to this section of the board right here, these holes are all connected this way. So these 5 holes are all connected together. These 5 holes are all connected together, but no 2 rows next to each other are connected. So this one and this one are not connected. The reason we do that is that with this microcontroller plugged in, say I want to connect something to this D13 pin, this right here. I plug in my controller to this row, and then I plug a wire into the hole that lines up with that D13 pin. And then I can take that to wherever I need it, whether I'm plugging it into a sensor module, to a resistor, or just tying it to ground or a switch or anything else. We split it down the middle to make sure that I have access to these pins. If I were to put this whole component, this whole microcontroller over here to where one side of it was on this row of pins and one side was on that row of pins, it would be shorting this pin with this pin, so they would have electrical connection between them, just like I stuck a wire between them. Same thing here and here, and that would actually end up in most cases just destroying my component. You don't want to do that. Alright, so let's talk about how we're going to actually use the soldering iron. It's very important to have somewhere to place the soldering iron so that it doesn't burn or melt anything. To be able to effectively melt solder, you need to be able to run it up around 600 degrees Fahrenheit roughly. I usually run it about 640 degrees. At that temperature, I'm going to melt plastic, I'm going to burn wood, and it's going to burn you without even thinking about it. So most soldering irons will come with some kind of a stand. This is the one that I use, modified because I broke it at one point and had to rebuild it using a coat hanger. Hopefully yours are in a little bit better shape, but you want it to where it'll hold up the soldering iron out of the way so that the tip doesn't touch anything that's going to burn or melt, or that you're going to touch with your own hands. The scrubber brush here is actually really important. If you look closely at the tip of the soldering iron, it's not bright shiny silver. In fact, there's some black crud on the end. What that discoloration is, the black is actually the burned up flux. It's carbonized, it's pretty gross. And then as you heat the metal, it actually oxidizes. Basically it's rusting. So as you work with it, if it gets covered up in that oxide, the solder doesn't stick to things, it doesn't heat very well. So you need to be able to clean that off. That's what this is for. Sometimes it'll just be a sponge that you'll wipe it on, a wet sponge. This is just a metal chore boy that you can use to scrape it off. And then to get the oxide off, you can pull in a piece of solder, and when the soldering iron's good and hot, I should be able to touch the solder to it and have it almost instantly melt. And you'll notice a little bit of smoke. That smoke is the flux melting or burning, and where the flux burns off, it cleans up the tip. And you can see as I put a little bit of solder on there, it'll stick to it, and I can kind of scrape off the oxide. You want to have your tip to where the solder will stick to the whole tip and it's nice and shiny. That's called tinning it. Put a nice little thin layer of tin on the tip of the soldering iron. The reason you do that is that when I go to heat a component, if I just have the tip of my soldering iron, it's like trying to touch something with the very tip of this. It just doesn't touch very much area. And the smaller the part that touches, the less heat goes. And I'm going to have a hard time getting the component hot enough to melt the solder. So we actually put a little bit of solder onto the tip of the soldering iron, clean off the excess, and then I'm going to go solder. And then every so often as I'm soldering, I'm going to come back here and I'm going to wipe it, clean off the tip again. Now when I'm not using it, I'll set it down and let it go. As far as temperature goes, for most applications you probably want to be running at about 600 degrees Fahrenheit. Solder will melt actually somewhere in the neighborhood of 200 or so degrees. Depends on the composition, what they made it out of. But if the soldering iron's not hot enough, you won't be able to heat up the part fast enough to be able to melt the solder with the part, and you'll actually end up heating up the whole thing a little too much, and you can actually damage the component, you can damage the circuit board. Alright, let's talk about solder for just a second. Hopefully we can make this focus. So this is what they call rosin core solder. And if you look at the very front, I'm looking through the magnifying glass on my bench, you can see there's a little hole in the center of the wire there. That is full of rosin. Rosin is a fluxing agent, and like I said before, rosin or flux cleans the component. Cleans off the oxide, makes it so that solder will stick. Solder does not stick to anything other than real clean metal, and only certain metals at that. In our case, it's copper, tin, and lead. That's just about it. If you try and solder aluminum, you're going to be mostly frustrated, and it just flat out won't work. It doesn't stick. So again, you got inside both of these is a little bit of flux that when you melt the solder, the flux runs out, burns, and then eats away at any oxide and contamination. You'll notice that these two are different sizes. This wire is much thinner, and I use this for very small components. I'll use this for working with surface mount, for example. And this one's a little stiffer, a little bit easier to work with, and we'll put down more solder for things like soldering pin headers onto sensor boards, or like the Arduino that I'm going to demonstrate a little bit later today. It's not super critical. The one thing you do need to watch out for, though, is there's different kinds of solder. These solders are both made out of about a 60% lead and 40% tin composition. Where it is made out of lead is toxic. It's bad stuff. You don't want it in your body. So how do we deal with that? Number one, you can see I'm handling it with my hands. There's not really a good way around that. You could wear gloves, I guess. But you don't actually absorb a lot of lead through your skin. Especially if you take precautions like washing your hands after you've handled the solder. So you always want to wash your hands, and usually you're going to get a recommendation to wash your hands with cold water. If you use cold water, the pores on your skin stay tight and closed so you don't get lead into the pores of your skin. Soap and water, and they'll take care of that. The other thing that'll happen is when you're soldering, you're going to see some fumes and smoke. Most of that smoke is the rosin, but you still probably don't want to be breathing that and having your face down in it. You can buy fume extractors, which are little fans that will pull the smoke through a carbon filter and try and get rid of it for you. I've never had that. I would say it's probably a good idea. However, my approach is to have good ventilation. I make sure that I'm not in a confined space. I try the best I can not to be face down over the top of it, so I'm sucking in the fumes. Other thing to know is that not all solders are suitable for work with electronics. If you go to Home Depot or Lowe's or any other hardware store and buy solder, more likely than not it's going to be an acid core solder for soldering plumbing pipes. That acid will stay behind and it will eat away at your components. You really don't want that. You want to make sure that you get a rosin core solder designed specifically for doing electronics. The last kind of solder, or there's two more types of solder I'll talk about. One is called silver solder, and so it's mostly lead and tin like this, but it has a quantity of silver in it, and it's specifically to deal with some issues that you can have with surface mount components in terms of the migration of silver that's in the component, causing cracking, losing connections. I forget the other reasons. It's not super important. Silver solder will work for general hobby use if that's what you have access to, but it tends to be more expensive because it does have silver in it. And then there's lead-free solder, which is almost entirely tin. It's like 93 to 95% tin. It'll have some copper in it probably, maybe a little bit of silver. Most of the components that you buy today are going to come with what's called an ROHS certification, and a part of that means that they're made with lead-free solder. Lead is a pretty bad substance to be in the environment, and we throw away a lot of electronics. We don't really want to throw away a bunch of lead and contaminate things. So the solder that you can buy for if you want to be lead-free is mostly tin. It is a little harder to work with. It does tend to crack a little more and has worse mechanical properties. I use traditional 60/40 lead tin solder. And that's what I recommend for general purpose, especially when you're learning. Something that's pretty important when you're getting ready to solder is to make sure that the joints are really clean. This is a piece of wire that I actually scavenged out of a tree in my backyard that somebody had used for an antenna. It had been out in the weather for a long time. Looks like the water has gotten down inside the insulation here. And if you look at this copper, there's kind of like a black layer to it. There's also kind of some sticky, greasy stuff to it. All of that is going to get in the way of having a good, clean solder joint. If you were trying to solder a wire like this, your best bet is to clean it up. Sometimes you can cut it off and strip back a little farther, but looking at this, I'll tell you that corrosion and that contamination pretty much goes all the way throughout it. If I can avoid it, I'm not going to solder with something like this. You know, just as a comparison, here's more bright copper with the solder wick, and here's the copper that's been oxidized and contaminated. Makes a pretty big difference, and it really makes a difference because the solder just flat out won't stick to this. Now flux will help clean some of it up, especially if you can get the sticky layer off, and I'll try and show you that here in just a second. Alright, so you're going to experiment with me. I haven't tried this with this wire. This is pretty gross stuff. It might not work, but I'm going to go ahead and put some flux on it, and we'll heat that flux up and see what happens to the copper. So my soldering iron's good and hot at about 640 degrees Fahrenheit. I'm going to bring it in. I'll tin it up just to make sure I have a nice good surface area to touch the copper. And you can, if you listen, you might hear it sizzle. Now if you look at the copper over here where the flux has heated up, you can see that it's cleaned it up pretty well. And then here the solder that was on my soldering iron has sucked down into the copper. It's called wetting, where it's basically pulled itself down like water in a wick and pulled along the edges of it. So that actually cleaned up pretty well overall. You know, if I come over here and heat it up, you'll see that to some degree it's going to clean up that gross black stuff. And you get a little bit better copper here. Now this had more of kind of the greasy, slimy stuff on it and less oxidation, and I think that's probably why that's not cleaning up quite as well. Now something you need to be aware of when you're working with solder is that the purpose of the solder. So solder's a metal. If you touch this across the terminals of a battery, electricity is going to go through the solder wire and back into the other end of the battery. It's probably going to get pretty dang hot. If you stuck it in an outlet, did something stupid like that, it would start a fire just like anything else. But lead and tin, which are the main components of this solder, don't actually conduct electricity all that well. What you're doing with the solder is not conducting electricity so much as gluing together the copper pieces that are already in place. The best you can, you want to have the mechanical connection already in place between the two conductors, and then the solder just holds it all together and keeps moisture out, keeps corrosion out. So I'm going to teach you a couple of quick splices and ways that you can make connections with wires that'll kind of demonstrate what I mean. Alright, I'm going to teach you how to join two wires. These are very stiff wires, more like you would find in the wiring of a house. But it'll be a little bit easier for you to see what I'm up to. Because these are stiffer and heavier, I'm going to use a thicker set of needle nose pliers. You can actually use, it's called lineman pliers. They're more like a flat kind of wire cutter that you would see for an industrial setting. So this is called a lineman splice, or I think Union Pacific splice, if I remember right. They used it to join wires on the telegraphs. Now if you're going to string a lot of wire over telegraph, you need it to be strong so that when you're pulling the wires apart, it doesn't come apart. You also need a good electrical connection because they didn't always solder them. So the way you do a lineman splice is you strip 2 wires back. Now this is excessive, you don't really need them this long. You cross them at about this area and you're going to bend to 90 degrees on each of them. So one's going up and one's going down. Then what you'll do is you'll wrap one wire around the other, keeping the coils close together like this, and you can actually grab a hold of that with the pliers to tighten it up. So I'm going to grab it here and I'm going to wind it up just like so, and you'll wind it around until the end piece is kind of tucked up and in like so, like that. Once that's done, I'll come on the other side on this piece and I'll do the same. I'll wrap it around. Now in this case I'm running out of wire. I didn't plan very well. I'm going to make several loops around. So now I've got this wire hooked onto that one, this wire hooked around that one, and this becomes a very strong joint. And at this point you really don't need the solder so much, because as it sits, I have the copper touching the copper, which gives me the connection, and it's got a very strong mechanical connection between them. Now, what solder will do in this scenario is it's going to keep water and other contaminants from getting inside that joint and keep it nice and clean and weatherproof. So what I'm going to do is I'm going to bring over my helping hands to hold this in place so that I don't have to do it with 4 hands myself. That's going to hold it here. Put a little more in frame for you. Now we're going to solder. This will be the first time we've done this. Now one of the most important things to know about soldering is that you're not heating the solder. The soldering iron is not there to make the solder hot. The soldering iron is there to make your part hot, and then you're going to melt the solder with the part. So to get good contact, we'll do like I said before. You can scrape off the contamination on the tip, clean the tip. I'm going to tin the tip with just a little bit of solder so that I have a good connection. The part that I'm soldering, and it might take a little bit, and I'll add just a little bit of solder to the soldering iron. You can see it's actually cooled off the tip of my soldering iron because it's sucking the heat out of the soldering iron. So that should give me a pretty good contact. I'm going to get a lot of heat building up. It takes a minute. As it does, it'll eventually get to where when I touch the, see there, then the solder starts to melt a little bit, and I'm going to just gradually melt the solder into the part, and you can see it kind of pulls in and gets nice smooth connection. It's called wetting, where the solder actually pulls in into the cracks and fills them in. And I'm going to come over here and hit this area, this side of it a little bit. One of the hardest things with copper is that copper conducts heat very well. So if I heat this part, the heat gets pulled very quickly away from it, which makes it an excellent heat sink, so keeping parts cool. But it's actually really hard to heat it up. It takes a lot of work to get it hot enough because all the heat here is getting spread out. At this point, these ends over here are going to start getting hot. And I'll just gradually move over, but you can see how I don't have big blobs and balls of solder in here. That's because the solder has wetted in. I started with clean copper, I heated the part, and I applied the solder to the part. The flux inside the center of the solder cleaned the part and wetted the solder all the way through. And what I could do is I could keep going on and do that all the way across this. But you see that how that looks, where it's kind of pulled down in, it's smooth, it's filled up the cracks. That's really what we're looking for with solder. We don't want big balls of it. We want enough to fill the holes. So that's the lineman splice and soldering 2 wires. Alright, so I'm going to show you how that works with a much smaller wire. This wire is what you would see something like connecting the switch on a garage door opener to. I think that's actually where I got this. This was left over from a garage door opener. I'm going to strip off a little bit more of the insulation and expose some bare copper wire. I have another one here that's already exposed. I'm going to cross the two. Leave enough room for the coils around it. I'm going to wrap this one around this wire. Wrap this one around the other wire. And I can either take my pliers and push those over, or I can take my cutoff clip, my wire cutters, and just clip that off. And I'm going to do the same on this piece right here, just clip that off. So now that I've got my splice made, I'm going to solder it. I'm going to clip it in my third hand to keep it nice and steady and easy to get to. Now notice how much faster this heats up with the same temperature on my soldering iron. I haven't changed anything. So again, I'm going to wipe the dirt and crud off my soldering iron. I'm going to tin it with just a little bit of solder. I'm going to apply some heat to the part, and already it's hot enough that you can see it wetting the solder all the way across. Now if you hold it on there too long, it'll start melting the insulation here, and you can see the insulation will start pulling backwards away from it. So you want to get the heat in quickly before it spreads too far. Apply the solder and then get off of it as quickly as you can. And when you're done, it should look kind of like this. Now let's take a look at it with the magnifying glass, if I can make that happen. A little bit better picture here. So you can see that the joint itself, the solder has flowed over the whole thing. It started to fill in some of the cracks, but I haven't added so much that it's bulgy or drippy or anything like that. And that's soldering 2 wires. Another common task you're going to have is soldering something like a resistor to a circuit board. So what I have here is a small piece of what's called perf board, perforated board, that has some copper traces that are already on there. There's a whole bunch of holes drilled in it at that same 1/10 of an inch spacing like you had on the breadboard. This is designed so that you can stick parts into it and then solder wires along the back of it to connect pieces together. So this is kind of like a breadboard, only a little more permanent. This is just a tiny little piece that I had left off of another project, but it's going to work great for putting the components in. This is a resistor. This one happens to be a 100 ohm resistor. If we haven't talked about it yet, we will pretty soon. We'll talk about what that means. I need to be able to plug this into the board. So there's a couple ways you can do it, and it depends on the circuit board layout. Sometimes they do what's called an axial mount. So you'll fold one of the leads over, so it's like this, and the two spaces will be, the holes will be pretty close together. So you stick the lead down through the hole like that, and you want to put it all the way down to where the end of the resistor is flush against the board. Now you need to hold it in place. So there's a couple ways you can do that. My favorite way is I'll grab my needle nose pliers and I'll bend the lead over like so. And at that point it's not going to fall out, it'll stay put. Another technique for mounting the boards is to mount them flat. Now sometimes you'll see where the spacings are very wide, so you'll have a little bit of lead left, and you'll take your pliers and put a 90-degree bend in the wire on both bends so that the length between the bends matches the spacing between the holes. I don't want to be quite that wide here. I'm going to bend it right about here, bend it down, make sure my leads are fairly straight, put it in the board, figure out where my other hole's at so I can see right about there. I'll grab it with my pliers and put the next 90-degree bend in it. I'll take and slide it down in the holes. Sometimes my fingers work better, sometimes the pliers work better. I got that too close together. Like that. Now if you put the sharp bend in it with the pliers, it'll look a little cleaner, a little more like a professionally done board. You can just pull the wire straight in and bend them over, not a big deal. Just like before, I'm going to take these leads and I'm going to bend them outward to hold them in place. Because I don't like holding it with my hands while I'm soldering, I'm going to put it on my third hand here, just using one of them. Now the trick here is I need to be able to heat both the lead of the component, this wire here, and the circuit board trace that I'm soldering to. So I'm going to take the tip of my iron and I'm going to kind of wedge it to where I'm touching both at the same time. let it sit for just a second to collect some heat, and then I'll apply a little bit of extra solder. So I've just cleaned my tip. I'm going to put just a dab of solder on the tip to tin it. And I'm going to put that dab of solder touching both the pad and the lead. So I'm going to heat both the circuit board trace and the wire at the same time. And I'm going to add just a touch of solder to the component, and then pull it off. And I want to let it sit. Don't do anything to it until it is cooled off. It does take a second for the solder to solidify. Now, a good solder joint, you should be able to see the solder kind of crawling up the lead a little bit and making a nice smooth connection, and then flowing down onto the circuit pad. Now, on a lot of circuit boards, there's going to be kind of a clean area that's either just bare copper or it'll be tinned like this. And all the rest of the traces are going to be covered with, it's called solder mask, kind of a green paint. You do want to fill up most or all of that exposed pad. Where this is a big trace of tinned copper, you can't really control how far it goes, but you do want to have good contact, good wetting all the way around it. We'll pull in on the magnifying glass and see if that helps a little bit with seeing it. Oh, come on, camera. There we go. So if you look in close at this, you can see that the solder joint has flowed around the wire, it covers the pad, and it flows up the wire. And once it's in, we're going to take the pliers and just cut off the tail right like that. You do want to wear safety glasses when you do that, because the wires can shoot pretty far and you don't want to catch one of those in the eye. With it zoomed in like that, I'll go ahead and solder that next wire, that next lead. So I've got my tip cleaned, a little bit of solder to tin it, put it on my component, and I'm going to add solder just to the wire and the pad until it flows and wets the entire pad just like that. When you're done, the resistor should be mounted nice and flush against the board. You do that by making sure when you pull it through and bend your leads over that you've taken all the extra slack out of it. Your solder joints should be nice and smooth, should wet onto the wire, onto the lead, and onto the pad. Okay, the next one is going to be working with discrete components. This is a little transistor. It's got 3 leads on the bottom of it. They're all spaced pretty close together, and you'll notice that those 3 leads don't fit 3 holes here. Almost never do they fit. I don't know why they do it that way, but when you have these components, you have to spread the leads apart. There's a couple ways you can do that. One, you're just going to grab it with your fingers and start to spread a little bit, put it in the holes, and shove it down. I'm not a big fan of doing that. It does work, but it does put a little strain on it. So what I do is I'll grab the lead with my pliers, I'll bend it out on purpose, right up near the base. You can see there's actually kind of a fatter part on the lead right here. I'm going to bend it right there until it's about where I want it, and then I'll jog it back like this. A couple of reasons I do that. One is that these parts tend to get hot and cold, and as they do, the leads will expand and contract, and that can actually break the solder joints. If there's a little jog in the lead, that actually can act like a little bit of a spring and help absorb and deal with that expansion without cracking the joints. Once you've got them set, just like with the resistor, you slide it in the hole, pull it down, and in this case we're going to go down to where those jogs are. Just like with the resistor, I'm going to fold the leads over just to hold them in place. You can go front to back, you can pull them left to right, whatever suits you, as long as it holds the component in place. Again, I'm going to use my third hand here to hold it in place. The rest of this works exactly like when I'm soldering the resistor. It's only now I've got 3 leads. So I'm going to come in here, I've just cleaned the tip of my soldering iron. I'm going to put a little solder on the tip. You can see it wet down. That means I'm hot enough. I apply solder until it fills the hole. Put my soldering iron there, put a little bit on, wait till it's to wet, add some extra. Put my soldering iron on, apply a little solder. As soon as it starts to spread and wet, add a little bit more. Last thing I do, I come in with my angled wire cutters, and I snip off the extra leads. Now you don't want to cut super far down. If you cut all the way down into the solder where the solder's flowed, you can actually crack the joint and weaken it. So just clip the extra off. That's all you need to do. Right, so one of the last things I'll show you comes in handy when you buy sensor boards and Arduinos or Arduino knockoffs, microcontrollers off the internet. A lot of them, especially the lower cost ones, will come just like this. You have the circuit board with all the main components soldered onto it, but it's missing the connectors that you would plug into the board. They're called a pin header. And these are just metal pins that have already been tinned with solder and have a plastic piece that holds them spaced out at the right distance. They're all very even size. And what you have to do is solder this pin header onto the circuit board. Now, doing this to the third hand could work, but it's going to give you kind of a challenge. Ultimately, I want to be able to plug it into this board, which means that I need these two pins to be very close to a specific distance apart. If I just looked at doing it by hand, if you look at this, I can tip it that far or that far, anywhere in between, and the odds of me getting two of them nice and square and lined perfectly up are really pretty bad. I've soldered a couple of these by hand without doing this, and I never was able to get them stuck into a circuit board without having to like mechanically bend the pins. So what you can do is you go ahead and you plug your pin header in straight into the circuit board. Right, like that. And then you set the Arduino or the sensor board or whatever it is that you're soldering on top of it. That way the pins are held upright by the board, they're held at the right separation, and gravity keeps your Arduino on there. And then all I have to do is do the soldering some. Alright, so just like every other time, I'm going to clean my tip, get myself a little bit more solder out here. Apply just a touch of solder to the tip of my soldering iron, and I'll place my soldering iron where it's touching both the pad and the pin, and I'm going to touch solder to the pin until it goes, and then I'm going to apply solder until it sucks down. Now, one of the things that's kind of unique about modern circuit boards is that those holes have copper all the way through them. It's like a little tube of copper with a pad on the top and a pad on the bottom, and when you apply solder, it's actually going to suck it down through that tube to the bottom half as well, and you got to fill up the crack. So I'm going to put enough solder to get it hot, and keep adding it until it's full. Some of these I tend to go a little overboard with. It's better to have just a little bit of a bulge on the connection than to not have enough solder in there. So I'm going to put it on here, apply the solder, let it warm up just a little bit more, and just keep adding a little bit of solder at a time until it's sucked down through. You do that working your way along until you've got all of the connections done. One thing you want to be careful of is keeping your fingers away from the tip of that iron. It will burn instantly. In fact, it tends to burn so quickly that it turns the skin kind of a white color. You don't want to get burned with a soldering iron. If you get a little bulb of it because you got too much, you just kind of wait, and it'll usually, as the heat passes through, it'll pull that bulb, that extra bulb of solder down into the joint. Just like that, and then the other side works the same. You just turn it around and keep going. Alright, one last thing. If you have a piece of copper that looks like this is a piece of circuit board that hasn't been etched. It's just fiberglass with a little bit of copper on the top and on the bottom. And it's been sitting long enough that there's some corrosion here from various things, some chemicals that it was exposed to. If you tried to solder to this, it's not going to work very well. You can try and use the flux to clean it off, but it's best in this kind of a scenario to clean that off first. And there's a couple of strategies you can use. One of the first that I'll use is just a pencil eraser. Sometimes that's enough to rub it off and give you a clean surface to solder with. The next one above that, you can use like a Scotch-Brite pad or a Brillo pad, or you can use like a Chore-Boy, kind of the metal sponges that you use for the kitchen sink, steel wool. If it's really bad, you can use some fine grain sandpaper like 220 or 300, 400 grit sandpaper, just real lightly. You don't want to take off all the copper, because if you make the copper too thin, it doesn't work. It won't conduct electricity very well. So if you see connections that look like this, kind of goobery and dark, ugly, clean them up before you try and solder them. Alright, that's it for today. Your assignment is to go work through your practice soldering kit. The instructions will be posted on the forum. Good luck, and let me know how it goes.